Hey, Katie.
Hi, Ben.
So we've had a lot of fun episodes recently. I'm just wondering if maybe we could have a normal episode,
Like a regular episode.
a regular episode. Yeah. Like you're listening to Linear Digressions. That was a bad pun because we're going to talk about regularization. Is that what it's called?
Yeah, that's what it's called. Regularization. This is one of the things that I use every day. Not everything we talk about is something I use every day. Regularization is one of those things. So, a lot of times when you're doing something like machine learning or statistics, there's usually kind of an assumption that's baked into a lot of these algorithms when they were first being put together, which is that when you're thinking about the data that you have to train it, you have many more samples in that data than you have attributes of each sample. So another way to think about that is if you have a table that has all your data in it, and each one of the samples that you take, or each instance, each training case is a row, and then each attribute of that training case is a column, you have many more rows in that table than you have columns. So
Right. So that's like you do a sample of three attributes of people and you sample 1,000 people. That's 1,000 rows and three columns.
yeah. And so for a lot of machine learning applications, that's actually a really nice, and statistical applications too, it's a really nice regime to be in because you have sort of a lot of chances to get familiar with the patterns in the data. And the patterns aren't so complicated that you don't really have enough data to like fully explore the space. Like the data very much like gives you the full picture of what's going on, and you can
Right.
start to learn the patterns in it, right?
Yeah, and so like if you look at, for example, the ages of your 1,000 people, you're very likely to get a nice normal distribution of ages. Whereas if you only had like 10 or 20 or 50 rows, or in other words, 50 people, then your ages will be a lot less, I guess, consistent with reality if you weight them normally, right? Because you might get a lot more older people than younger people just by random statistical chance.
Oh, I see. Yeah, so I hadn't even been thinking about that, but yeah, there's sort of two things in there, and let me just
Hmm.
tease them apart a little bit.
Yeah.
So the thing that you were just talking about, if we only have 50 rows in our sample, let's say, then yeah, we're in a regime where it's very likely we're going to run into kind of statistical fluctuation. So in general, when you have just not very much data to begin with, that's always going to be a tough place to live.
Right.
And what I'm talking about is something that's slightly different, although sort of related. I'm talking about the scenario where you can have lots and lots of data, perhaps, but it's more about the ratio between the number of rows and the number of columns. So even if you have,
Ah.
let's say, 1,000 samples, if each one of those samples has 1,000,000 features, then you're still in a regime where even though you have 1,000 samples, that's a lot of data. Well, it's sort of a lot of data, but it's definitely 1,000 is much less than 1,000,000, as you're well aware. So even though we have, 1,000 in and of itself, if you had three columns or something, 1,000 might be just fine. But the fact that you have 1,000,000 columns means that 1,000 is not fine.
So I guess you're kind of talking almost like so I work with graphics, and so I'm almost thinking of this as the aspect ratio of your data. If rows is the height and columns is the width, if your data is a lot wider than it is tall, you're going to have to interact with it differently, very differently, than if it's more tall than it is wide.
Yeah, yeah. And I think that even if you have plenty of rows, even working in spaces where you have high dimensionality can just be tough. Even if you have, let's say, 1,000,000 examples that you can learn from and 1,000 columns. So we're flipping things around now, and it seems like we should be very happy. If you're going to try to build a model with, let's say you're building a regression or something, a simple linear model with that, that means that there's potentially 1,000 different features that you think can affect your outcome. And that's kind of a lot to keep track of. Like, let's imagine that you were trying to explain to your boss after you built this model what it is this model is doing. Well, you'd have to tell him 1,000 pieces of information, or her, tell her 1,000 pieces of information before she had the full picture of what this model is trying to tell you. And that's just kind of a lot of things to keep track of. So,
Right.
yeah.
It's also just, I mean, even if you can get the computer to kind of grok all of this stuff, it's really hard to understand it as a human and to convert whatever your model is doing into, I don't know, like a dissertation or a report to your client or whatever it is.
Yeah, so depending on the regime, it still might be something that is perfectly valid. And in general, this is not a hard and fast rule that there's any maximum number of features you should be thinking about. But yeah, if you want to try to interpret this, or if you want to tell some kind of story, especially if you're trying to model something that should be kind of intuitive and you want it to be graspable in a way that, not everything always is, but sometimes we want it to be something that is understandable, and usually 1,000 features is not a particularly understandable place to be, right?
Right.
So, okay, so working with high dimensional data is it's got some tricks.
And so we're talking about regularization, which I'm guessing is taking that high dimensionality, the large number of columns, and trying to find a way to minimize that.
Yeah, so regularization is a fairly specific way of doing that dimensionality reduction. There are several different big classes of dimensionality reduction that you can think of, depending on exactly what you think about perhaps like the internal structure of the data and how you want to privilege certain types of data relative to other types of data. But yeah, regularization is sort of one of the really big ones. One of the things that makes a lot of sense to just sort of throw regularization at it and let it sort it out. So regularization, there's a number of different names for the different kinds of regularization algorithms. So you might hear this referred to as GLMs or generalized linear models, which is actually a bigger set of models than just regularization, but sometimes people refer to those things kind of in the same way. You might hear it called lasso regression or ridge regression or elastic net regression. These are all types of regularization. But in general, what regularization is going to do is if you're running an unregularized model, this is sort of something that you're going to run just out of the box before you're trying to do any dimensionality reduction. What that model is going to do in the course of fitting is it's trying to come up with a formula that will minimize the error on the predictions that you make. So it's trying to find the equation that's going to predict each one of your cases with as small of an error as possible. Mm-hmm. And what regularization is going to do is it says, we want you to simultaneously take into account how big the error is of your model, but also the complexity of the model. And the complexity of the model is basically how many of the features are you actually using in the model.
Got it. So rather than just saying, hey, do your best and minimize the error, you're saying do your best, minimize the error, but also look at the complexity. You don't want to have crazy complexity with very little error. You might actually be willing to accept a little bit more error to have significantly reduced complexity.
Yeah, and so exactly the way that it trades off between the goodness of fit and the complexity, that's what makes those different kinds of regularization different from each other, lasso versus ridge versus elastic net, blah, blah, blah. But in general, the thing that they have in common is there's this thing called the regularization parameter. And that basically trades off between how important it is for you to have a model that fits the data very closely versus a model that's simpler. And so the stronger the regularization parameter is, that basically penalizes you for adding more complexity to the model. So you're still allowed to add more variables, but they just better be really darn good. They better really help your the goodness of fit of the model in order for it to sort of overcome the penalty that you pay for adding it in.
Right, that makes sense. So it's just kind of trying to do that cost-benefit analysis in a good way.
Exactly. And so what these regularized models are going to do, each of them is a little bit different in the details of exactly what it does, but they'll select for you I'll pick lasso regression because this is the one that I use the most. Lasso regression will actually just entirely throw out parameters that don't pass the regularization scheme. So you can take, let's say, 1,000 features, dump it into a lasso regression, and depending on exactly what the strength of the regularization parameter is, it might only send back a model that has 10 or 20 or 50 or 100 variables in it. So it's actually throwing out a whole lot of the data.
Yeah, it's throwing out like 90 to 99% of it in a lot of cases.
Yeah. And so again,
but, if the data it's throwing out doesn't actually strongly change your path, then it doesn't really matter.
Right. So it's saying, again, you're allowed to have more data. It just has to sort of earn its place in the model. And if it's not making the model better by a big enough margin, then it's not going to get selected. And it's kind of interesting just to give a little bit of background about lasso. So the place where this becomes really important in the real world, to the best of my knowledge, is in genomics. Because each person, if you're trying to do genomic analyses, let's say you're trying to study correlations between the genes that you see in someone's genome and various types of proteomics or symptoms that they have of some specific disease or whatever. There's potentially many, many genes that can be responsible for the phenomenon that it is that you're studying. And you don't necessarily know which ones are the important ones, so you want to be open to the possibility of any of them. So you want to have this very high dimensional input space because you have all these genes.
Right, of course. And it's also difficult to get this information, so you're not going to have 1 million people. You're going to have a lower, I guess, number of rows.
Right, yeah. So you think about the context in which these studies usually happen. It's a small research team that's maybe working in one hospital or one university. And so they only have the ability to collect maybe 100 genomes or something like that. And there's potentially millions of different genes that they're studying. So they're very much in this regime where there's many more columns in their data set than there is rows. And so in general, there's all kinds of things that you have to be careful about when you're working with this data. Regularization is just one of them. And I hope that in some future episode, we'll pick up some of the complexities of things like hypothesis testing when you have very high dimensional feature space. But for just tackling the problem of what features just seem to be relevant to this problem, like the first order problem of what should we even be paying attention to, something like regularization is going to be one of your best friends.
Okay, Katie, what were those normalization algorithms you were talking about again?
Oh, regularization, you mean, but...
Oh, excuse me.
Yeah, no, it's fair enough. I used to get those two mixed up all the time, honestly, when I was first learning this. So
Actually, this kind of illustrates my point. I just remember you mentioned so many of them, and I was thinking, gosh, like, could I be a data scientist knowing that I constantly get words confused and I constantly get the names of things confused? And I mean, I guess it's just that it's not my field, and in my field I'm a little bit better, but I mean, what has that journey been like?
Oh, yeah, no, that's a good question. So the first thing that I should say is that when I'm doing this podcast, I pick the things that I feel comfortable with to talk about. So you're getting a biased sample of the areas of my expertise.
I see.
So that's the first secret. Is
because you always sound really smart.
I pick topics somewhat carefully.
Right.
And yeah, no, it's a really good point because there is a lot of jargon, and obviously, the more familiar you get with this field, like any field, you just become familiar with it and you get to know it, and it's not as scary anymore once you know what's working under the covers. But if I'm being completely honest, so I was talking about a number of different regularization schemes. I talked about lasso, I talked about ridge, I talked about elastic net. We didn't talk about the differences, but I just kind of ticked them off my fingers.
Mm-hmm.
And so I said there's differences in exactly how they calculate what complexity means. And this has to do with technical details. There's something called like an L1 norm and an L2 norm, and that has to do with the size of the coefficients of the variables that you're putting in the model. And all this is to say that L1 and L2, I think, are very undescriptive names. And I didn't know that, it's not that I didn't know the difference of them, but one of them is lasso and one of them is ridge. And
oh, interesting.
I honestly have like a little cheat sheet that sometimes I have to refer to remember which one is which. Because, when you use them a whole lot, I guess now I know the difference because I use lasso so much that I just,
yeah, you use it enough.
Yeah, you just kind of like memorize it. But for the longest time when I was getting used to regularization and I knew that they both existed, but I just couldn't remember which one was which. And it made me feel kind of dumb because everybody's just like ticking the stuff off like it ain't no thing. But yeah, that's an example of something that I had to do this every day for 6 months before I was able to kind of fake my way through it adequately.
Right. Yeah, and actually thinking about it now, the same goes for me. So I'm a front-end web developer most of the time, at least in my professional career. And so I write a lot of JavaScript, and earlier on, I mean, if you ask me, okay, what's the difference between array.shift and array.unshift, I know that one of them puts something at the beginning of an array, and one of them takes something away, but I always got them confused. And then I started doing this consistently. And what's funny is just 2 days ago, I typed the wrong one, and I'm like, why isn't my code working? Everything's broken. It's just, like that's why documentation exists. It's not necessarily just so you can learn, but it's also so you can refer to things. And really, I think the most important thing, I guess, whether you're doing front-end web development or computer anything or data science or anything, is thinking critically about how to put things together rather than memorizing exactly the way to do everything. Because you can always look up the latter, but the former, that's kind of where the art of it, takes over and where you need a human to do it.
Yeah, I think that's totally right. Especially, I think data science, this can be particularly challenging because data science isn't a pure field. It's like a little bit of computer science and a little bit of statistics. And then there's machine learning, which is kind of got elements of those both as well. And it borrows ideas from that originally came out of fields like economics and physics and all kinds of other stuff. And so it's just this big mishmash, and you can end up having ideas that are fundamentally really similar, but that have different names, and just depending on somebody's background, they might call it something completely different. And so I think that the vocabulary challenges in data science can actually be a lot more significant than in some of these older, purer fields, because it just it hasn't been around long enough for there to be a dominant vocabulary that's really taken hold.
Linear Digressions is a Creative Commons endeavor, which means you can share or use it any way you like. Just tell them we said hi. To find out more about this or any other episode of Linear Digressions, go to lineardigressions.com. And if you like this podcast, go ahead and leave us a review on iTunes so other people get to listen to this content too. You can always get in touch with either of us. Our emails are ben@lineardigressions.com and katie@lineardigressions.com in case you have comments or suggestions for future shows. You can tweet us at lindigressions. Thank you for joining us, and we'll see you next time.